All right. Good morning, afternoon, or evening, everybody. Welcome to the CSDA Vendor Focus MDA Space NASA Commercial Satellite Data Acquisition Program webinar. This is your host, Jennifer Brennan. It is 2 p.m. Eastern Daylight Saving Time, so we are going to go ahead and get started here. I will begin today's webinar with just a few logistics. To ensure the best audio experience, all participants have been placed in silent mode. But if you have any issues or you have any questions, what I'd like for you to do is enter those into the Q&A panel rather than the chat, and you should see this located on the right side of your screen. If you do not see the Q&A panel, you can click on the three dots at the bottom of your screen to pull up your panel options and then insert a check mark next to the panel option. A quick word about the chat. Excuse me, participants will have the capability to chat with the hosts and presenters, but not with all participants. So again, if you have any questions, we really would like for you to enter those into the Q&A panel on the right side of your screen rather than the chat. Today's webinar is being recorded. The recording will be made available online within a week of completion. And then once completed, what I will do on my end is send an email to all registrants and participants that includes links to both the recording and presentation slide decks used within today's webinar. As far as timing is concerned, today's webinar will be 1 hour and 15 minutes long, with 45 to 50 minutes allocated to the presentations. A 15-minute Q&A period will follow, and depending on the volume of questions we receive, we may extend the Q&A session, but we will have a hard cutoff at 3:15 p.m. Eastern Time. During this afternoon's webinar event, we will have one speaker from NASA CSDA Program and two speakers from MDA Space. Excuse me. Our first speaker this afternoon is Dana Ostrenga. Dana is the CSDA Program's project manager here at NASA's Goddard Space Flight Center. She will begin this afternoon's webinar with an introduction to NASA's CSDA Program and its objectives, and will then provide a high-level overview of the CSDA program vendor MDA Space, its IDIQ contract, and data access. Once finished, we will transition to our vendor speakers for this afternoon. Our first speaker is Stuart Blundell. Stuart is the Senior Director of New Business Development for the USA for MDA Geointelligence. He will kick us off with an introduction to MDA Space, its company history, and RADARSAT heritage, and provide a preview of the upcoming CHORUS platform. From there, we will transition to our second speaker this afternoon, Gordon Staples. Gordon is the Senior Radar Application Scientist and Project Manager at MDA Space. He will continue today's presentation with a comprehensive overview of the currently available C-band RADARSAT-2 data products available through NASA's CSDA program and discuss use cases for the products. Once finished, he will toss it back over to me and I will open up the final optional webinar feedback questions. And at that point, we will transition directly to the Q&A session. Before I toss it over to Dana, I'd like to say just a few words about this afternoon's Q&A session. We will try to answer all questions within the time allotted, but if we are not able to address your question during the Q&A period, our speakers will be able to follow up with you offline. So with that, it is my pleasure to introduce today's first speaker, Dana Ostrenga. Dana?
Good afternoon. Can you hear me okay?
I can hear you.
Fantastic. So good afternoon, everyone. I'm Dana Ostrenga from NASA's Commercial Satellite Data Acquisition, or CSDA program. Today, I'll talk a little bit about our program and our partnership with MDA Space. Next slide. So NASA has a really strong history with Earth observation data. We acquire it, we enhance it and build products. We utilize the data into our research and applications. We steward that data for dissemination. And NASA really wanted to explore the possibilities of acquiring and integrating commercial data with our agency partners to support all of our research and application initiatives. So with the increasing numbers in commercial Earth observing constellations, and we wanted to leverage all of their newer technology, providing higher spatial resolution, shorter revisit rates, and tasking capabilities. And it really makes it all ideal to incorporate their data into our ecosystem and augment our existing government satellite data. Next slide. So CSDA's mission is to establish a cost-effective, repeatable pathway for identifying, evaluating, and acquiring that commercial data that support the Earth science objectives. We aim to provide a continuous on-ramp process for our commercial partners so that we can increase the capabilities we receive from the commercial space. We want to be able to enable sustained scientific use and dissemination across our broad user community and stakeholders. And we want to ensure preservation and reproducibility of the data that we acquire. We also want to coordinate with our interagency international partners on the evaluation and improvements of that data from all of our commercial partners to increase interoperability and facilitate use and integration into applications. Next slide. So we're really working across a broad and rapidly expanding commercial ecosystem. This just showcases our diverse array of commercial partners currently on contract, providing unique satellite data products to help NASA advance Earth science. We currently have 15 commercial vendors on contract that we can acquire data from. For multispectral imagery, we partner with Vantor, BlackSky, and Satellogic. For Planet, they operate in both multispectral and hyperspectral domains, alongside Teledyne Brown Engineering and Pixel, who specialize in hyperspectral data. Another one of our vendors, Airbus, operates both in multispectral and the area of synthetic aperture radar, alongside our other SAR providers, which include MDA Space, Umbra, ISI, Capella Space. They all enable weather day-night imaging. And for monitoring methane emissions, we go to our provider, GHGSat. For GNSS radio occultation capabilities, they come from Planet IQ and Spire. And then for digital precipitation radar, we utilize the data that's available from Tomorrow.io. So together with all of these vendors, it really enables NASA to access high-value commercial satellite data across a broad range of Earth science applications, really enhancing our ability to monitor and understand our planet. Next slide. So a key enabler is our end user license agreement framework. So at a minimum, CSDA requires a USG government license, but we prioritize license that explicitly allows scientific, non-commercial use, data sharing, and derivative product generation that aligns with acquisition practices from other agency partners like NRO. The idea is that once we know a data set is scientifically valuable, the broader community then can actually use it at scale. So to make this sustainable, we're really increasingly relying on standardized licensing templates. And this is just one of those examples of how this has been implemented in our program. Next slide. In CSDA, evaluation is really central. So we conduct independent science-driven assessments of commercial data to understand performance limitations and the appropriate use. So our evaluations are carried out by a distributed science team across NASA centers and partners, with domain experts aligned to optical, SAR, thermal, hyperspectral, DNSS, and other domains. Each leads different methods and conducts the analysis, ensures alignment with existing standards and best practices, including those that come from ESA's EDAP and Joint Quality Assessment Framework, which I'll touch on in just a moment. Our evaluation framework looks at 5 key areas, which is accessibility, metadata quality, user support, data quality, and data utility. And for accessibility, we really look at how easily users can discover and retrieve the data, including integration with tools like NASA's Satellite Data Explorer. For metadata, we examine completeness and adequacy. So for scientific interpretation and traceability and uncertainty assessment. For user support, we assess the responsiveness and technical competence when issues arrive with using the data. For data utility, we really ask whether the data that advances NASA and community Earth science objectives or fill specific observational gaps. And finally, for data quality, we really focus on geometric accuracy, radiometric performance, calibration strategy, and how well uncertainties are quantified in line with current principles. So these dimensions, ensure that data is not only just high quality, but stable and interoperable in practice. These evaluations build trust inside NASA and externally. They support interoperability by explicitly testing how well commercial products integrate with agency missions and their CalVal infrastructures. All the resulting evaluations, once they're available, are publicly released, so that provides transparency and documentation, and in fact, kind of gives that community an awareness into how the evaluations are conducted and what the results are. Next slide. So as part of our evaluation process, just wanted to touch quickly on the ESA-NASA Joint EO Mission Quality Assessment Framework. That really builds on ESA's Earth Observation Mission Quality Assessment work that they have done, and we developed jointly agreed guidelines. For example, we just released last year the SAR guidelines, and we just signed off on the optical guidelines. The framework really standardizes evaluation criteria, and it kind of provides a common grading approach and enables cross-agency comparability for both agency and commercial missions. So this will provide transparency to our commercial partners as well on the whole assessment process and the methodologies that are used in assessments, and then enables the scientific community to understand that evaluation process and easily compare evaluation outcomes. Next slide. So we continue in CSDA to expand our partnerships. We really do this to improve our data sharing, our evaluation alignment, and acquisition coordination. We have a really strong, close relationship with the JC that has multiple federal agency as stakeholders within the JC framework. We continue to align our collaboration with ESA and participate in the joint evaluations and development of guidelines with them. And then we also have coordination with other sectors of our federal government in not only data acquisition, but data evaluation. Next slide. So that brings me now to talk a little bit more about CSDA and MDA Space partnership. In January 2025, CSDA awarded MDA Space an IDIQ contract under our On-Ramp 1 RFP solicitation. Through this effort, CSDA was able to leverage existing evaluations and a really extensive use of RADARSAT-2 SAR data for our CSDA subject matter experts. They were able to conduct an in-house evaluation of the data and better understand MDA Space's data products. That evaluation results were briefed to headquarters and to MDA, and they were placed into what's known as a sustainment. When you're in sustainment, then you're allowed to compete for competitive task orders. They were awarded an additional task order for SPANSAR data, so we have that available to our stakeholders for tasking. Any data access that is received will be available through the CSDA Satellite Data Explorer. And if you qualify under one of our EULA structures, you can register for access to the CSDA website. The SDX, or Satellite Data Explorer, really provides a central web interface for search and discovery of all the data that's distributed by CSDA. So this ensures easier access for researchers and smoother integration into the rest of our data systems. Next slide. Recently, we released our data acquisition request system. So if you have an interest in the MDA space data, want to take a look at that or any other data that's on contract with CSDA, you can put a request in through the Satellite Data Explorer. On the left-hand side is the access button for the data acquisition request system, and you can make your request. We are currently bringing on new business through another on-ramp through our IDIQ contract vehicle, and hopefully those new contract partners will be available before summer. We're continuing to grow our collaborations with our federal partners as well as our international partners to expand the use amongst our scientific communities of all the data that's available through CSDA. Next slide. So that brings us to the next part of our webinar. To our speakers today, talk more with us about MDA Space and their capabilities. So Stuart, I'll stop sharing and you can take it from here.
Thank you, Dana. Thank you. On behalf of all of my colleagues at MDA Space, welcome to today's webinar on RADARSAT-2. RADARSAT-2 is a polar orbiting synthetic aperture radar satellite operating in lower Earth orbit, capable of imaging day or night in all weather conditions. As you will learn today, the spacecraft, now in its 18th year of operations, has remarkable capabilities for imaging in over 20 different beam modes at different spatial resolutions and with multiple polarimetric options. As Dana mentioned, MDA currently has an active task order with the NASA CSDA program to support disaster and emergency programs responding to floods, earthquakes, landslides, and other geohazards. Next slide, please. One of the first startup space companies, MDA's origins began in the basement of John McDonald's home in Vancouver, British Columbia in 1969, which led to the creation of McDonald, Detweiler and Associates. MDA is now one of the fastest growing space companies in the world, with over 4,000 employees providing satellite manufacturing, robotics, space operations, and Earth observation services. In March of 2026, MDA was listed on the New York Stock Exchange. Next slide, please. The RADARSAT program is a series of Canadian Earth observation SAR satellite missions initiated in 1995 with the launch of RADARSAT-1. RADARSAT-2 was launched on December 14, 2007 as a joint project with the Canadian Space Agency and MDA. There are now over 1.6 million RADARSAT-2 images available in the archive to qualified NASA CSDA participants. CHORUS is MDA's fourth generation satellite SAR constellation, which will be placed in inclined orbit and provide both C-band and X-band imaging for tip and cue collection requirements. Next slide, please. As Gordon builds this out, as shown here, the CHORUS SAR satellite constellation will provide unique tip and cue architecture that enables broadband monitoring of the world's oceans and classification of vessels. CHORUS is expected to be operational in early 2027. At this point, I will turn over the presentation to my colleague Gordon Staples to walk you through all of the incredible capabilities and applications of the RADARSAT-2 satellite.
Okay, so good afternoon, morning, evening to people, and thank you, Stuart, for the handover. I will now talk about RADARSAT-2 and look at some of the sensor and data characteristics. So a little bit of background on radar. With radar, there's always a balance between spatial coverage and resolution. So this is one of the wide swath RADARSAT-2 modes. This is a ScanSAR wide. This is Vancouver Island off the coast of British Columbia. And just in context of that, if you put this tip of this island in Vancouver, it would extend as far as Portland, Oregon. So ScanSAR mode is characterized by a 500 by 500 kilometer swath width. Just for brevity, I'll just refer to it, I'll call it the swath width 100 meter resolution. That mode is commonly used for Arctic mapping in the Antarctic and the Arctic as well. But you can see the pattern here that as the spatial coverage decreases, the radar resolution goes up. So just walking down here, you go to standard mode, 100 kilometer swath width, 25 meter resolution. There's standard mode here, this one. You go down to the quad polarized mode, 25 kilometer swath width. There is a 50 kilometer option as well. 10 meter resolution in here. And then the highest mode we offer is Spotlight for a number of reasons. There's a little bit of an imbalance in here, but the size of this image is approximately 18 kilometers by 8 kilometers. One of the innovations that was done during the early days of RADARSAT-2 is that a number of modes were added to the satellite after launch. And in the design of RADARSAT-2, MDA had built in that capability. And based on a demand to get wide area coverage at higher resolution, and in contrast to what I said, the extra fine mode was developed. And this mode is really interesting because you get 125 kilometer swath width at 5 meter resolutions. 5 meter resolution. Now, there are a couple of things done to achieve that. But for the most part, this particular mode is widely used because of that high resolution and the good spatial coverage. The takeaway on this is that there's always that balance between spatial coverage and resolution. Going on now to the polarimetric capabilities, just a brief contextual diagram here, cartoon. There are two fundamental polarimetric modes on RADARSAT-2. And there is a horizontal and a vertical acquisition mode. Horizontal, more or less, the satellite beam, the radar beam is parallel to the Earth's surface, and vertical, it is vertical to the Earth's surface. So we have three fundamental imaging modes. There is a single polarized mode, and in those particular modes, the user can specify the acquisition of a horizontal transmit or horizontal receive. There is the corresponding, you can transmit horizontal and receive vertical, or you can transmit vertical and receive vertical. So these are termed copolarized, these are cross-polarized, and this is the copolarized. So once again, typically it's our high resolution modes, but this is available as single polarized only. There is the option for dual polarized, and you can get that with a copolarized and the cross-polarized. The key advantage here is that you are receiving two images acquired at the same time, but in different polarization states. And if you relate that to a simple analogy, maybe not simple, but to the optical world, with radar, the frequency is constant, but when you vary the polarization, you acquire different information about your target, and it is somewhat akin to looking at different frequencies in the optical domain. And finally, there is the quad polarized mode, and this provides the most polarimetric information that you can get from RADARSAT-2. So there are 4 images acquired at once, the 2 co-polarized, the 2 cross-polarized, and the key piece of information that is retained is called the interchannel phase data. And that phase difference is essentially the difference between the travel time from the time the radar leaves, or the radar beam leaves the satellite, goes to the Earth and back to the radar. And if you look at that difference for the 2 co-polarized data channels, there is target-specific information embedded in that. So this is an incredibly rich source of polarimetric data. A couple of examples here. This is an ice image showing the horizontally polarized and the cross-polarized. And the driver for the polarization capability was driven by the fact, as I was talking about, is that additional information in the image. RADARSAT-1, which was launched in 1995, was a single polarized sensor. It was just horizontally polarized. And when RADARSAT-2 came along, a lot of work was done to look at the capabilities. And one of the first groups to really jump on the board with dual polarized data was the Canadian Ice Service. There was also the counterpart in the United States, the National Ice Center. And you can see here the big difference there is and the additional information you get. You have the horizontally polarized image here. There is ice information in there. This is the same image acquired at the same time, and this is the cross-polarized image. It's very likely that this is first-year ice, and it's moderately smooth, and a smooth surface generates typically a relatively weak cross-polarized return. So you can see that feature here. There are a lot of features in the ice that show up extremely well in the cross-pol, and you might miss them in the co-polarized. And similarly, there are maybe features in the co-polarized that may not show up in the cross-pol, but the combination adds that much more information. The example here shows, this is a quad polarized image, a wetlands mapping. And there's been a target decomposition algorithm applied to the quad polarized data. And there's a variety of target decomposition algorithms. There's the Cloud-Potier, Freeman-Durden comes to mind. And these algorithms are applied to the data, and they're able to pull a lot of information from the data and relate that to some of the classification, some of the features that you're looking at. But this is a wetland area here, and it's just been colored for visualization purposes. But the areas here in red are characterized by wetlands, wetland areas, and relatively strong radar scattering. And the reason for that is that this is Phragmites, which in some cases is an invasive species. But the radar energy comes in, it bounces off there's some attenuation, but it essentially reflects off the weeds back to the water and back to the radar. And that will generate a strong radar return. And that's visible here in terms of this red coloring. In this area, this is a low-lying area, perhaps unvegetated ground or a little bit of water to some degree. And then the green area are agricultural, just routine agricultural areas. So again, with this quad polarized data, you're able to extract a lot of information from a single image. So RADARSAT-2 has 2 look directions. It has two look directions. So primarily, the look direction is to the right of the satellite travel direction. So on an ascending mode, the satellite is traveling northward, and the satellite is looking toward the east, roughly. And on a descending mode, the satellite is flying southward, and it's looking toward the right again, and that's roughly toward the west. There is a capability that's called a slew maneuver. And the idea of a slew maneuver is the satellite will transition from right-looking to a left-looking configuration. So going back to this descending mode here, instead of the satellite coming down this way and looking right, it has the option to look left. And one of the key advantages of that, if you were responding to a disaster or a flood, for example, and let's say, for example, you're coming down this part of North America, and if you just had the right looking, you could image that way, and that's it. But if you wanted to get that additional data, and that flooding, for example, was in this part of the country, you could switch to a left looking mode, and acquire an additional image. So go through some of the characteristics of the satellite. It was launched December 14th, 2007. It is a C-band radar with a nominal wavelength of about 5.6 centimeters, nominal altitude of 800 kilometers. The resolution varies nominally from about 1 meter, which is the spotlight mode, to 100-meter resolution, which is the ScanSAR wide. Variable imaging size, and again, I mentioned this 2 or 3 slides, that there is variation in the spatial dimensions of the satellite image, and that in turn drives the resolution. But with the highest resolution spotlight, it's about 18 by 8 minimum size is the minimum size, and the ScanSAR wide is about 500 by 500 kilometers. The orbit is a sun synchronous dawn dusk with about a 98.6 degree inclination. And one of the key messages here is that our products are all linked to UTC time, but if you're in the field, roughly speaking, it depends a little bit with latitude, but if you're in the field doing field work, for all intents and purposes, we image at about 6 a.m. in the morning and 6 p.m. in the morning local time. That changes a little bit as you go farther north or you go farther south toward the poles. But the key thing is that we know in advance where the satellite will be imaging at any given time. We have a very deterministic orbit, and we can tell you where we image at what time next week, next month, or next year. We have spent a lot of time, a lot of effort over the years to maintain the orbit tube, and I have a couple of slides coming up on that. But for the last 10 or 12 years, the orbit tube has been plus or minus 150 meters, which is ideal for INSAR and other applications. The exact repeat is 24 days. So if you're looking at doing INSAR, for example, or doing change detection, typically you would want to use the exact repeat of 24 days. There are some other ways around that to improve that a little bit in a process called intertrack. But so by looking at that, the satellite comes back to essentially the same position in space, and then the changes you measure, for all intents and purposes, are related to the ground and not to where the satellite is in the orbit. There's also the term of the revisit. So the revisit is when can we come back to a certain area and image that area. So at equatorial latitudes, roughly speaking, it's nominally about every 2 to 3 days. It varies a little bit. And as you move toward the polar latitude, because of the fact that it's a polar orbiting satellite, as you move closer to the polar latitudes, you have that much more imaging opportunities. And roughly speaking, it's about at least daily. I talked about the polarization, so the single polarized, the dual polarized, and the quad polarized mode. We have 20 imaging modes. There's the one spotlight, that is our highest resolution. We have the 15 strip map, and then there are 4 ScanSAR modes, which are the wide area coverage. In terms of the image products, we have the spotlight and the strip map, and there are 3 key products for that. There's a slant range single look complex, and the single look complex data is typically used for applications such as INSAR and polarimetric data, because both of those data require access to not only the detected, or sorry, the amplitude data, but also the phase data. Most of our data is detected data. So you basically strip out the phase information and you just have an amplitude product, and that is a ground range detected. There's also a geocoded detected, which adds a little bit more geometric accuracy to the product. ScanSAR is processed as a ScanSAR image, and it is only available as a ground range detected. So when you look at all the RADARSAT-2 imaging modes, there's all kinds of them. I'm not going to walk through all of them, but just looking at them in terms of the resolution, these are the ScanSAR modes out here. Variation from, maybe 300 kilometer swath width to 500 kilometer swath width. Resolutions on the order of 50 to 100 meters. And a lot of these modes are used for ice mapping, maritime surveillance. We also have modes that are optimized solely for ship detection, and they do a fantastic job for ship detection over wide areas, but they're somewhat limited for other applications. You then move into the modes here, and this is where you have, these are dual polarized modes for the most part. The modes go into here, there's dual polarized, there's the quad polarized modes. And these modes offer resolutions from about 25 meters to about maybe 10 meter, roughly speaking, and various combination of these modes for various applications: disaster management, land classification, crop monitoring. And then you get out into this area, and these are the higher resolution modes. And these are resolutions less than about 10 meters nominally. And the corresponding spatial coverage is reduced because of that balance between resolution and spatial coverage. And so a lot of these modes are used for when you want very target specific or information over a relatively small area with very high resolution. So land intelligence, mapping, resource monitoring, forest change, for example. So we spend a lot of time with image quality and calibration. And I have been with MDA for a long time. And I've been involved in the RADARSAT-1 mission, RADARSAT-2, the RADARSAT Constellation mission, and the forthcoming CHORUS mission. And from the start of RADARSAT-1, there was a lot of work put in, not only to the ground system, I'm not necessarily talking about that, but also in terms of the image quality. And one of the key parameters there is just having that radiometric quality such that if you take an image that was acquired 5 years ago, a month ago, and an image you plan to acquire 2 years from now, if you're looking at a target that isn't changing, you're going to pretty well be within plus or minus half a dB of the radar response. So that's actually incredibly good radiometric stability. We go through a process of throughout the mission, RADARSAT-2 with very stable image quality. All of the RADARSAT-2 modes have been calibrated, but we take about roughly 5,000 images a year, and these images are acquired for image quality and calibration analysis. And we have two procedures for that. We have corner reflectors that are installed, and the corner reflector is typically it's metal, and it's maybe a diameter, a size here. There's one here, for example. It's maybe 1.5 meters this way, roughly speaking. And these corner reflectors are a specific shape. This one here, you can't see it, but it's a trihedral. And they produce a known radar response. And that known radar response is then compared to what the satellite is actually measuring. And then that is adjusted via some of the calibration parameters. So the these corner reflectors are used for resolution assessment, for other radar parameters, side lobe ratios, and also for looking geolocation accuracy. We also use the Amazon rainforest to look at distributed target measurements. And it's somewhat surprising in a sense, maybe not surprising, but the rainforest itself is a very, very homogeneous target. And so a lot of the variations that you get across the image, I mean, they are related to some degree to what's called the radar incident angle. But beyond that, you get some very stable radiometric information. And that information is looked at things like the radiometric accuracy, beam patterns, beam pointing, polarimetric collection matrices, and a number of parameters here. But the key message here is that the combination of corner reflectors and the Amazon rainforest allows the image quality and calibration for both resolution issues and also other parameters related to radiometry. So in terms of some of the improvements that we have done over time, we've looked at improving the geometric accuracy, and a lot of this is just driven by the demand for INSAR. And so the solution for that was to develop a tool that was called the Enhanced Definitive Orbit Tool, or EDOT. And this was used, it uses a variety of different sources of information from other sources of information, using that to improve the geolocation accuracy. And the result of that is that there was a significantly improved orbit maintenance over the satellite and much more orbit control. And if you look at that, at launch, the ground track maintenance was plus or minus a kilometer. So that was 2007. 2008 to 13, there were some improvements, brought it down to plus or minus 500 meters. And then after the implementation of EDOT, the orbit tube has been maintained at plus or minus 150 meters since 2013. This says 2025, but it's through to today, fundamentally. So going on now, if you look at data availability and RADARSAT-2 information, as Dana had mentioned, this for the new acquisitions anyway, but in terms of accessing the data, you initially have to get the CSDA authorization form, and then the CSDA team will verify that and then go forward from there. In terms of the RADARSAT-2 availability, we have archived data from from 2008 to present. And that data has been acquired in various sites around the world in different imaging modes. And there's also the ability to acquire new acquisitions. And Dana mentioned that at the beginning through the process to go through that particular process. In terms of online viewing of the RADARSAT-2 archive, in addition to the NASA system, there's also an interface that was developed and maintained by MDA. And you can read it here, GSI portal, MDA Space, Explore. And that will give you access to where the data has been acquired. And embedded in that is a thumbnail image that gives you an idea what's there. So this is the actual tool. And it always helps to have a guide. So there's also a guide that will guide you through the process. There was also a mention of the evaluation process. So RADARSAT-2 data was evaluated by NASA and approved for the CSDA program. And the link for that is here. And in addition to the report itself, there was a lot more information that goes through all the RADARSAT-2 imaging modes. And it gives you imaging mode information on resolution, noise floor, and other things like that. So depending on what you're doing, that more detailed information may be of value. One of the important parameters to consider is the difference between archive versus new acquisition. So if you have archived data, that data, somebody acquired it, they've defined the imaging mode, let's say ScanSAR. They've defined polarization, say it's a dual polarized. They've defined the incident angle the data was acquired at, and they've defined whether it's an ascending or descending mode. So those parameters, and there were other ones as well, but those parameters are defined at acquisitions or defined when the data have been acquired. So when they've been acquired, you cannot change those parameters. This is what you get, that's it. Not surprisingly, if you have a new acquisition, you define the imaging mode, the polarization, the incident angle, ascending, descending, et cetera, et cetera. So that is completely user specified. But one of the nice things is that independent of whether the data has been archived or a new acquisition, the data can be processed. The data are processed after the acquisition. So let's say, for example, there was a bunch of data that had been acquired, and maybe it's listed in the archive as a detected product, but other than ScanSAR and ScanSAR modes. But if that, say it's listed in the archive as a detected product, that data can be reprocessed and converted to a single look complex. So say, for example, there is a detected product, you can't do the INSAR with that, but that data can be reprocessed, even if it's been in the archive, and processed as a single look complex, and then you can use that for INSAR applications. So just an overview of the archive itself, roughly 1.6 million acquisitions from 2008 till early 2026. Huge amount of effort along coastal areas in North America, the Arctic, not too surprisingly, over various parts of Africa, Asia. We've done a lot of imaging. Some of this is for applications related to forestry in the rainforest, but also a lot of calibration. A lot of imaging in Antarctica, and in certain parts of the oceans we have very limited imaging there. But the key thing here is that you have an idea where the data have been acquired from an archive point of view, and then one could go in there and look at that data. And in some cases, there may be a very deep time series of data, and you can augment that with other data sources. So we'll go on now and look at applications for NASA Earth Science research. And starting out with just looking at just an overview of RADARSAT-2 applications. Ice mapping was probably one of the most mature applications of radar, RADARSAT-1, RADARSAT-2. And it all, as I think I had mentioned, but it really drove the design of RADARSAT-1. There was an interest by the Canadian government going back to the late 80s, where they wanted to look at Arctic sovereignty. They wanted a sensor that gives all-weather day-night imaging to support navigation and shipping through the Arctic, hence radar, and hence the choice for ice mapping of the wide swath modes. This example here shows a time series of RADARSAT-2 data over a five-day period. And there are 4 RADARSAT-2 images here. And what we did here was just highlight the ice edge. And the interest here, there was a vessel coming along. This is the Beaufort Sea coming in here to drop off supplies to some of the communities. This vessel did not have an ice strengthened hull. And so the captain of the vessel wanted to know where the ice edge was to find out, was it retreating? Was it advancing? Could they come in, drop off their supplies? In terms of some of the application benefits, so I just mentioned ice extent mapping to support safe shipping, looking at changes of ice cover and linking that to global warming, and ice condition to support transportation of food sources to northern and, for that matter, southern communities. Another big area is looking at illegal fishing, and we have a number of programs now. We were looking at illegal, unreported, and unregulated fishing. And one of the big data sources for that is radar. So this example here, this is in the East China Sea, and the bright dots here are ship targets. Generally over the ocean, a ship produces a bright return, and for the most part, the ocean is moderately dark, so there's good contrast. But you see clusters of vessels here and here, and that's an indication of fairly intense fishing. Now, some of it's legal, some of it's illegal. I'm not going to get on that road, but nevertheless, part of this, looking at this fisheries monitoring, is to look at what's going on and assess, is that legal or illegal? So in terms of the application benefit, so I talked about illegal fishery. So taking that information from the radar and combining that with AIS data, RF transmissions, and optical data, that gives a really quite a full, robust picture of what's going on, and then looking at that for looking at sustainability of fishing stocks. And also another application of ship detection is just ship traffic monitoring, environmental sensitive areas, and also for coastal sovereignty for various countries. Carrying on the maritime side of things, looking at bilge dumping. So a lot of bilge dumping is fundamentally illegal, and it is a very characteristic return on a radar image. You have the ship here, appears as a bright dot. The generally weak response from the ocean surface, the presence of wind will make it brighter, makes it a bit more problematic. And this is a classic bilge dump, this dark return behind the vessel. And what oil does is it attenuates the small scale capillary waves on the ocean surface, reduces the radar backscatter, and it appears dark. So the benefit here is mitigating the impact of bilge dumping to the ocean and coastal zone, coming from bilge dumping, offshore pipeline leaks, offshore oil spills. And the radar data alone is interesting, but similar to the illegal fisheries monitoring, by combining the radar data with AIS data, automatic identification system, you can look at a vessel, and if it's has its AIS on, it's leaving a bilge dump, which maybe isn't the smartest thing. But if you have the AIS on and a bilge dump, you can go back and correlate the bilge dump with the vessel, and then the information on the vessel or registry from the AIS data. Flood mapping. So this is one of the drivers for this particular task order in terms of disaster response. Again, it's quite a mature application for radar. This is a pre-flood image. This is a post-flood image. We've gone through here and identified the areas that have been flooded. And typically what people want is not 2 radar images, but they're looking for the changes. In this particular case, they've been highlighted red. but it would be very straightforward. Well, not straightforward. We can highlight it for visualization, but typically for an end user, you would digitize the flood extent, say into a shapefile, and that information is overlaid on other information related to critical infrastructure, hospitals, roads, airports, etc. Application benefit, I mean, flooding is flooding, but detecting flooded areas and the impact to critical infrastructure, but also looking at the impact to food supply. So for example, in Asia, a lot of effort goes into agriculture for rice monitoring and for rice production. And depending on the type of rice that has been planted, certain rice can withstand being flooded for longer periods of time and not suffer any mortality. So if you do have a flood and you are monitoring that, and let's say the flood occurs, it lasts for a week and a half, in that particular area, it's okay because that rice is not going to, have more high mortality rate. But if you had sustained flooding for weeks on end, there may be a much greater mortality rate. Another example here on agriculture, this is soybean crops in Brazil, and this is a central pivot irrigation, hence the circular pattern here. And in this particular case, the two crops up here have been harvested. And so you've gone from a little bit stronger radar return when the vegetation was present into this area is moderately smooth after harvesting, so it appears dark. And so these have been harvested. This one is probably just ready to be harvested. The benefit here, in addition to monitoring crops in general, but certainly monitoring crop growth to support food security for domestic needs of a given country. So if you have an excess of certain types of crops, that's good. But if you don't have enough, you may have to go in to the open market to buy it. And if you know in advance what your production is going to be, it allows you to buy or sell in an optimal manner. Finishing up here, look, forest harvesting. This is another big application for radar. We've done a variety of projects around the world where we will work with various forest companies to monitor the harvesting that's going on. This example here is in Indonesia, and this is a plantation forest. And I live in British Columbia, Canada, and we have a lot of forestry here. But if you were using radar to monitor forest growth, it's like about a 40-year cycle from harvesting, planting or harvesting, planting, and harvesting a second time. So it's a pretty long time to wait. In contrast, in equatorial areas, the trees are planted and they're anywhere from 5 to 7 years, and then they're ready to be harvested. So it's a much quicker cycle. But this example here just shows this is the area of the forest set aside for plantations. This area had been harvested, and these bright returns here are the presence of stacks of the timber that's been stacked into place, ready to be awaiting shipping. And that stack of timber produces a relatively strong radar return. The benefit here, monitoring harvested areas to ensure compliance with, say, environmental regulations, but also looking at the impact of carbon storage, that if you remove a forest and replant it, your net carbon difference is not quite zero, but close to zero. But if you remove a forested area and put in industrial or something like that, then you've lost basically that ability for carbon storage. Finishing up with land deformation, INSAR. And it's a really interesting example here. This is in Seattle in Washington State. And there was a underground roadway being built here, and there was a tunnel boring machine that basically got stuck. And what was done here to retrieve the truck was a process called dewatering. And essentially, dewatering is that you put pipes into the ground and you remove the groundwater. And you remove that groundwater, which relieves some of the pressure on the tunnel boring machine. But you've also taken away the presence of the water, so we have that subsidence. So a very pronounced example of that, and it's really quite a very practical and a very useful example. Application benefit, so talking about stability and safety of critical infrastructure, and also looking at deformation in coastal zones that could be impacted by rising sea levels. And there's a host of other applications for INSAR as well. So finishing up here is just looking through how RADARSAT-2 complements NASA Earth science priorities. So these are some of the priorities here surface dynamics, cryosphere, sea level rise. And what I did was to look at the various features of RADARSAT-2 and how it maps. So the various beam modes, polarization, incident angle, wavelength, the orbit control, so our orbit tube, and also the image quality. And for the most part, you know, virtually all of the features do map quite well to some of the Earth science priority, but some of the ones that seem to be a little bit of a winner here, but the availability of all the different imaging modes, the orbit control, which is good for INSAR and just geometric accuracy as well. And then also the fact that, in my view, that this image quality and calibration, that there's, as I mentioned, a lot of work has been done to ensure that there's stable radiometry and good quality geometric control. And that's it. And thank you.
And so I think the first question that was noted was actually in the chat. And so it's more of a comment, but maybe Dana, you could address this. So the comment is neither MDA or RADARSAT-2 are listed on the CSDA application form unless I am missing something. Could you speak to that a little bit? And I also see with the acquisition request system that that is not an option either.
Thank you. Yeah, I really appreciate you bringing that to our attention. We'll make sure to get that addressed right away. And so hopefully we can get that added before the end of the week.
All right, perfect. Thanks so much, Dana. Just let me take a look at the Q&A. All right, so the next question is the 5G interference a problem for your land imaging? If so, what percentage of the data is impacted in recent years, and can these interferences be mitigated?
It does occur, and that's in something that you really can't control. So whether it's land-based, we sometimes have interference with other spaceborne radars. Now, the interference with the other spaceborne radars is known in advance because we know when the orbits are crossing. In terms of land-based, that is not always noticed, but built into the processing algorithm, there is a check that is made to look for the presence of interference. Now, you have the interference, so you can't do much about that, but at least if there is interference detected, then that image will be noted. And if an end user has requested it, they'll be informed that there is some interference there. Now, that's kind of a double-edged sword because sometimes you don't want interference, and other times you're thinking, okay, I'd like to find out, you know, why there's interference and what's going on. In terms of the number of images, I don't know the number offhand, but it's relatively small. But relatively, it could be, you know, down in the decimal percentages, like 0.25% or something like that. I don't have that exact number, but we can follow up and find that number and let everybody know. But again, it's a very, very small number.
I do know that with the C-band, it's much, I know with the NISAR data that you've been seeing some interferences, and it's definitely not the same magnitude of problem as it has been with the L-band.
Well, really appreciate the additional feedback. Thank you, Gordon, for your response. And also thank you, Wendy, who is online from MDA Space as well as a Q&A panelist. Thank you both. I'm just scanning the chat to see if perhaps anyone had added a question there. Is the entire RADARSAT-2 archive going to be made available? And then what is the process for requesting new acquisitions after a disaster?
The answer to the available archive data, the answer is yes, it is available. In terms of the request for new acquisitions after a disaster, that process was mentioned by Dana at the onset, and I forget the exact acronym for that, but there is a process in there through NASA Explorer, I believe that's what it was called, to acquire the new data. And I mean, if Dana, you can add the correct information to that. I was just going by memory there.
Sure. So Eric, and actually anyone that's interested for archive data, certainly reach out into the data acquisition request system. And like it's been pointed out, I've already sent communication to the team. They'll get that added to the system. So if you're interested in MDA SAR data, you can make that request to that system. You can also send us an email. We welcome that communication line. We'll try to get the data in the interim that you need. We do have the SAR task order right now for MDA Space, but if you have archive, which is a lot of tasking, but if you have an interest in archive data, then please, ask for that as well. So then we can also make some potential modifications to that acquisition to get that data for you.
If I just make a comment related to, I believe the opening question is related to disasters and floods. And typically with radar, it's pretty hard to do otherwise, but you need a before flood and after flood. And if there isn't an image before the flood, there isn't an image before the flood. So what is nice to know that if someone is looking at an area and there's a possibility, say it's an area that's known to flood or an area that you might expect to flood, knowing in advance that there is a so-called pre-flood image can be very handy because you're not wasting time trying to find that out. So it's possible, if you know the area, go into the archive, find out what is available, does that image cover the area that you might expect to flood, and then it's yes or no. And if no, it's no. And if it is available, then it's there, and you could acquire it and have that available, and then get the new acquisition to support the flooding, if and when it occurs.
Okay, well, thank you very much. Thanks for Dina's kind of recap on data access, and then also Gordon, thank you for your response. So I'm just taking another scan. At the moment, I do not see any additional questions, but I will fit a minute or two here. However, if there are no additional questions, what we will do is we will log off from the audio component, but I will leave the virtual meeting space opened for additional, optional. Oh, yes, Dana, you wanted to say?
I actually have a question.
Okay.
So I wanted to ask Gordon, so just to follow up on your flood analysis when there is a disaster, would it be just as helpful to have imagery of that area, like from multispectral sensors, or is it recommended to have a SAR image captured of that area as well as like a pre-flood?
I believe, I guess self-serving, the answer would be it has to be radar, but realistically, you could readily look at another data source such as multispectral, for example. And the interesting thing about flood mapping, or interesting, I suppose, may not be the right word, but in contrast to, say, INSAR, for example, and other applications where you need to have that exact repeat, with flooding, for example, because that flood response, it's such a strong difference between the pre-flood and the post-flood that even if you haven't got exactly the same imaging mode, or in terms of the radar, the same the incident angle, and with an optical image or multispectral, they're a little bit different. But when you compare them, you can do a little bit of image processing and at least get an idea where the flood is. And even if it's something as straightforward as identifying, you could co-register the data, identify where the flood is, and do a visual or a heads up digitization. Having that information, even though it may not be perfect, is better than having nothing at all, and then nothing at all. So you can take that digitized area, convert it into a shapefile, for example, and then somebody can, as I mentioned, take that, integrate that with their other data sources, and how does that flood extent, compare or relate to being the proximity to critical infrastructure.
Okay, well,
great, thank you.
Thanks so much to both of you. I do have a comment in the chat that I'd like to read aloud just to get some, get a pulse from the MDA Space folks. And so the comment is from one of our USGS participants: RADARSAT-2 data are available to the International Charter, but only as amplitude data. Education of the Charter Board needs to happen as complex data, which they deem as a research need, because INSAR results help forecast and prepare for ongoing disaster with regard to volcanoes. Any comments that you would like to, or insights you might like to share?
Other than saying it's certainly a valid observation. I would tend to think that with the disaster charter, the reason that the single look complex data is not provided, I don't know for sure, but this is what I would speculate, is that you don't always have the you don't always have the same imaging mode and the same incident angle, the same look direction. If you're just, like as I mentioned before, whether you're even looking at multispectral data. So typically with single look complex data, you don't need that single look complex data if you're just trying to take two images, different modalities, and trying to co-register them as best as you can, and then do a visual digitization of a flood. You typically don't need that. But based on the question, if you were looking at say volcanoes, for example, you're looking at changes to the Earth's surface, for sure you would need single look complex data if you're trying to do interferometric analysis. And again, other than, to me, that seems very reasonable, but I don't know all the nuances associated with the disaster charter, and I don't know fully why single look complex data isn't provided, other than there was a comment, I believe, that you read out, that it's considered more of a research initiative rather than an operational need.
And we may also point out that you demonstrated in your presentation, Gordon, that the data still exists. It can be reprocessed as a single look complex. So Julie, you're more than welcome to put in a request for the data to be reprocessed to single look complex.
Right, that's a good comment. I should remember what I say sometime.
Okay, so I do want to just note a comment that was made by Eric Fielding in the Q&A, and that is NASA does have a solution developed as a result of the Satellite Needs Working Group, and that is their NASA Opera project. And they produce a dynamic surface water extent, or DSWX is the short name for that data product, from single SAR images. He noted that having a pre-flood image is needed to see the change in water extent, but not the extent at the time of acquisition.
Yeah, that is very true.
I see also added some information here as well.
Yeah, no, that's a very valid point, that if you are just, I guess if you have other information of an area, and typically there might be other information, you could just have that one image and say, I already have maps and shapefiles of roads and rivers. I just want to know where the extent of the flood is. And so you map the flood, and then you look at what you already know and overlay that, and any areas that you perceive to be water that are beyond what you already know, I guess you could argue that would be the flood extent. But yeah, it's a very true comment, that you could map flood extent with one image, assuming that you've got other source of information to try to find out what is the normal distribution of water and other things like that, or spatial distribution.
All right, well, thank you very much for that, Gordon. Do you see a follow-up? Let me just, that was helpful. As a follow-up to the charter information, that was helpful. The charter offers the huge advantage of rapid and high priority tasking and download, and the charter won't deliver SLC. I will remember to request reprocessing outside the charter. Perfect. Yeah, thanks so much for all of this great input. We really do value the information that's being provided by our users.
But I just want to say that the limitations of the Opera project are that it's the data, the water mapping products are from Sentinel-1, which has a long revisit time, so it may be challenging to get the actual flood image from an Opera product, although it might make a nice normal water conditions map, except that there may be some resolution differences between what you acquire with the commercial data and the 30-meter Opera water map. So just a couple of points on the limitations of the Opera for some of the flood mapping work.
I would like to thank our speaker from the CSDA program, Dana Ostrenga. I'd like to thank our two speakers from MDA Space, Stuart Blundell and Gordon Staples. Also, thanks to Wendy Branson as a Q&A panelist, also from MDA Space, and my co-host, Joseph Smith. Thanks so much for the support. And more importantly, thanks to all of you for taking time out of your day this afternoon to learn more about the SAR data products available through MDA Space and via NASA CSDA program. So with that, we will log off from the audio component, and we hope to see you at an upcoming webinar. All right, I'll leave the virtual space open in case you think of anything. All right, everybody. Thank you so much. Take care now. All right, goodbye.
Thank you, Jennifer.
You're quite welcome.